recording the lecture. View. All right, can you see my slides?
Yes, we can see.
Thank you. Thanks a lot. Okay, so now we start the second lecture. I hope you had a good weekend and didn't work too much because now we are going to have to work a lot this week. There are lots of things you need to catch up with. And this first lecture, real lecture of doing real work is going to be focused on regression, which is one of the simplest things one can do in machine learning. Okay, so let's start with the beginning. What we want to do is to learn from data. And the idea, at least as physicists, is that we are going to try to understand nature. That's our focus of research. And to understand nature, we first need to observe nature. We need to look at it, we need to take measurements, and if you want, let's call all these measurements of these observations of nature a data set. And let's call this data set X. So some measurements, some observations of what nature is doing. Then, based on our observations, we would like to model what nature is doing. So we like to build a model, a predictive model that tells us that given what we've seen before about nature, if in the future, at any moment, we have some inputs, we are going to be able to predict the behavior of nature. We want to model that, okay? This model can be of many types. It can take inputs and deliver outputs. And there, the parameters of the model, how we set the coefficients you want that bring from inputs to outputs, we are going to call them with the letter W. Okay, but this is what we do as scientists, right? We look at nature, we observe it, we collect observations, and based on those, we try to model what we see, try to understand the inner workings of nature as to be able to understand more general laws of physics, and then to be able to predict new phenomena. Now, our modeling, how well we are doing, and we are able to describe nature, how well we are doing needs to be, if you want, quantified. When we contrast our model with the nature observations, we need to set up some kind of metric that says our model is really good or our model is not doing very well. Something that allows us to answer the question of how well the model, G of W, represents the data X. And the idea is that what we do usually is to try to find the parameters W that are the best representation of the data. Now, I know that this all sounds very abstract and maybe not super clear, so let's move to a particular example. Here, I'm showing a set of points, of measurements, that tell a relation between the distance and also the redshift. This is the Hubble law. You want the manifestation that galaxies, objects, that the universe is expanding. And that relation, which initially was obtained as the Hubble law, is a linear relation between redshift and effective distance, which is the y-axis. The data points are these red and yellow dots that you see over here. They come from different sets of systems like supernova and so on. I'm not an astrophysicist and I am not very knowledgeable of what goes behind this, but what I know is that it's quite messy and quite difficult, but once you get it, and you plot it in this way, which is redshift versus effective distance, you get a linear relation. Okay? So before we even had these lines on top, if you think on the data and the way it's represented, you will say, okay, my best model that represents a relation between redshift and distance is going to be a linear fit. And omega in this case, or W in this case, represents the best parameters, which means from all the possible lines that I could be drawing over here, the best line that fits everything is one over here. But it's best with respect to what? What makes, for example, this black line better than this yellow, this blue dashed line? What makes it better is some kind of criteria that you yourself put on your representation. For example, you could say that your criteria is that you would like your model to represent the data in the best way, and that for you means that the distance, average distance between your prediction and the data points had to be minimized. That will be the usual square error, for example, and you are trying to minimize the overall square error. But it could be that your criteria is that you would like to represent the data best, not just in this low redshift area, but you would like to be able to also encompass or give more weight to what is happening in the high redshift area, or over here, these red points. Whatever your criteria is, it tends to be a function that takes differences between your prediction and the data. This function, the function that we take as criteria and we try to minimize, is called, in this kind of language, a cost function. We try to minimize the cost of our fit, and this cost is a function of the data, of course, and the modeling that we've done, and also the parameters of our model. Minimization, then of the cost, what values of W minimize this cost function fixes precisely the best model. We are going to go over this example several times, so if maybe this is not super clear to you right now, that's okay. You can ask now or wait a little bit, and maybe in a few minutes you can ask me if this is not clear. But the concept of the cost function is simply what is the criteria you're going to use to decide what is the best model, and minimizing that cost function precisely fixes or gives you values for these model parameters. Now, when you see this kind of plot, to arrive to this plot, for people who work in this area, they know all the stuff that goes behind it, and they know it's quite involved to arrive to a plot that is so clearly linear. There are lots of assumptions, lots of modeling, lots of theory and experimental effort that needs to be done in order to obtain such a beautiful data, and in terms of parameters that precisely show clearly their linear behavior. So the fact that this plot was made by scientists, but people who knew what they were after, it took probably many iterations until they arrived to the point of being able to plot this redshift against this distance to actually see this relation. So there is a lot of human input, if you want, in order to obtain a plot that is clearly so manifest of some physical law behind. The fact that the galaxies are running away from each other, that the universe is expanded. And until we had a plot like this one, this wasn't clear, right? So there's a lot of human input in this, but even with the best intuition and the best scientists behind, we will not be able to obtain these kind of relations. We will not be able to unveil these physical laws if the data is not the data set is not large enough, and also the error bars were very large. Okay, here I'm just making the point that when we talk about understanding nature, observing nature, there are lots of components that come in. The observations need to be abundant enough and good enough. And then in order to actually see relations in those observations, some human input is needed. Some kind of intuition or understanding of fundamental physical laws need to go into this. And apart from that, there is yet another thing that one has to take into account, which is sometimes you have a fantastic data set, very large, and you have a fantastic understanding of what's going on, and your model fits extremely well, like is happening here. But then, because there is some kind of advancement in your experimental techniques or whatever, you realize that your model, that it was so nicely looking, is not generalizing anymore. For example, in this case, imagine that at some point, one will be able to shrink even further these error bars or go further in any other variable over here, where our linear fitting is no longer a good fit. So by extending the range, the number of variables, or shrinking the error bars, we might realize that our really nice linear relation is no longer true. As it happened, for example, in this case, when we realized, when I didn't, but the community realized that the universe was expanding, but instead of doing it at a constant rate, it was actually accelerating. And that led to the discovery of the acceleration of the universe, dark energy, and all what could be behind. This is something that goes beyond this linear relation that we see so clearly over here. So models, the models that you write down and you work so hard in obtaining, might not generalize well, meaning they might apply very well to the data you are seeing now, but when you apply it to new data and try to obtain predictions, those may fail. So in machine learning, there is a lot of emphasis on making models that are robust and they can generalize to new unseen situations. Why? Because there, the understanding of what's going on might not be as robust or as is in physics. Okay. Okay, so let's see this in some of these aspects with simple examples. Here, what I'm saying about generalizing models is the difference between being able to fit and being able to predict. Where is the difference? For example, here, we are showing a set of data points, 10 data points. Okay, on these panels on the left, what we have is the data set we are going to train on. So it's the data set we are going to use to minimize our cost function and find the best fit. That's what we are going to do. We are going to fit this data. And then once we fit the data, we are going to see how well it generalizes. So how well this data is able to predict a new unseen set of data points. For example, here, look at the range. It's from 0 to 1. That's where we are going to train. And we are going to test our predictions in a range that is slightly larger. So we are going away from the range of data points we were able to see before. Okay? And on top, what we are displaying is data points that correspond to a linear relation between x and y. So the truth is a linear relation. On the bottom, we are displaying points that have been obtained by imposing a polynomial relation between x and y of the 10th order. So a polynomial that contains components up to x to power of 10. Okay? So think for the moment that we are here, we are on the left, just training our data. We only have 10 data points. We depict x and y, and they're clearly linear. So when we try to fit with a linear polynomial, g of omega of w, our model is linear. So g of w is simply a constant times x. Then we get a line with a particular value for the constant. When we try to fit with a polynomial of a third order, so something that goes x to 0, x squared, x cubed, then we also get a line because the best fit is the fit where the coefficients of x squared and x cubed are 0. And the same goes for the polynomial of 10th order. So you see the three models, they all lead to all of the same predictions. The data is clearly linear. There is absolutely no deviation. So we get a good fit in any case. And then when we extend and say, well, okay, so now I know what is for each of these models. I know exactly what the best coefficients should be. Let's check that. And then I'm given this data set, and what I'm going to do is to set where is the best, I'm going to predict the values for this data set, and I get indeed a good prediction. So now let's do something a bit more complicated. We see a set of points. The points are these blue dots over here. And they have been created by producing some relations between x and y from a 10th order polynomial. That's why they are a bit wiggly. They go up and down and go up. So they have a more complicated features now. And what we see is that if we try to fit this data with a linear polynomial, so just something goes as x and a constant, the best fit will be some line that is like midway among all these points over here. A third order polynomial, this orange line over here, is going to try to capture those wiggles of going up, down, and up again. Not very well. And of course, if you then try to fit with a polynomial of 10th order, since the truth is that those features have been created by a polynomial of 10th order, the fit is absolutely perfect. And because the data set, although it's small, is just 10 numbers, but just enough to fit a 10th order polynomial, when we then test on a larger sample, the out sample is called, then we see that the first order polynomial, the linear, is not really good. Like it tries to keep it straight, whereas in this range we haven't seen is doing pretty badly. The points are over here, and this is the prediction for the linear. The cubic, which before had been trying to fit the wiggles, now it completely undershoots as well. And it's the 10th order polynomial that is able to then predict everything. And it's working very well. It generalizes very well. Okay? Now, life is not like this. We don't have 10 events that are perfect. Usually what we have is situations where our measurements have some level of error. So what happens if, and what we did before, we add error bars, some Gaussian error on the measurements, and to compensate, we also increase by 10 the number of data points. So since each of our measurements is no longer so precise, let's collect more of those and see what happens. So here we are going to do exactly the same. The truth is still a linear and 10th order polynomial. Our trained data set is going to be made of these 100 measurements with an error bar. And we are going to test on 20 measurements like before and the same kind of errors introduced on them. And then the situation changes because, as you can see, now instead of all the points lining up beautifully around a linear plot, we see how they scatter up and down. They have these kind of features that seem to be linear, no? It's some kind of, they are more or less around a linear the relation between X and Y, but as you can see, they are no longer so clear. Behind these data points, there could be many relations that we are not able to see. Although the truth is linear, so these data points, they should all line up on a line over here. We see them scattered, and that could tell us, or that could induce us to believe that there is some kind of interesting pattern behind this data. In fact, there is no pattern, there is just a linear relation, and is the error bars, is the fact that our measurements are no longer perfect that brings us to maybe believe that there is some pattern there to be discovered. Okay, so what happens in this case? Truth is linear. All these features we see, all this scattering is due to error bars. The linear plot goes more or less like this. So it's a straight line trying to be across the middle of all these points. The polynomial of third order also tries to do that. But something happens when you start trying to complexify your model, to make it more expressive. When you start adding more parameters to your model, for example, by going to a polynomial of 10th order, what happens is that this polynomial and the best fit to that data is no longer going to be just a straight line going across. It's going to start having these strange features. For example, it thinks that, or the best fit leads to this polynomial that can have borders over here. So it goes down here, it goes down here, it has lots of wiggles. The best fit to all this data for this polynomial is something that has lots of features. So you want what this polynomial, this complex model is finding is that there are patterns behind the data that are not real. Same happens here. Let me go back for a second. You see the data we are showing is the same as you can see here. Now with 100 points and with some Gaussian noise added on top. So you see now is a mess. We don't see that structure at all. So again, when we try to fit linearly, that's fine. The linear fit just tries to go more or less in the middle of all this scatter. The cubic starts trying to get some kind of pattern over here, going up and down just in. And it's the 10th order polynomial that also, obviously, tries to start, getting some features. So although the truth is a 10th order polynomial, exactly this one, when we try to fit a noisy set of data with a 10th order polynomial, what minimizes the cost function, the best fit to this data is no longer the 10th order polynomial we had at the beginning. This complex model with many parameters, this 10th order polynomial, is trying to fit features that are not there. So what happens is that those kind of models do not generalize well. They might be able to fit these relatively well. Maybe the cost function, and it's probably the case, the cost function for this polynomial of 10th order, the green line, is lower than the linear or the cubic. So it looks like we are fitting better the data. But when we ask those models to then generalize to predict an area they haven't seen before, then those complex models do not generalize well. I'm spending time with this because that's the problem number one we get in machine learning. Number one meaning the first that appears. Then you soon get used to deal with it, but it's like the typical problem. Models in machine learning are trained to deal with very complex data sets and try to extract features on those data sets that are hidden in you and that are not clear. So the problem number one is to let the machine learning model to run wild if you want and try to fit everything. There are so many parameters in, let's say, neural networks that this fit that they can do is extremely good. But the predictions they do, so how much they can generalize, is extremely poor. So we need to make sure that our model does not overfit. Here, another way of saying it is that this polynomial of 10th order is too expressive. So it has the ability to fit many features even when they are not there. And with noisy data, features might look as they exist and they are not there. So sometimes with noisy data, keeping on a simpler model, one with less features and being less expressive, as you can see here, is a better prediction of the data. Okay? Now, this is, you might say, okay, but what is the point then on increasing the complexity of our model if we are going to fall into this problem of overfitting? We get a very expressive model that can describe lots of stuff, and then we realize that it's actually running around trying to explain things that do not exist. The idea is that these kind of techniques are tailored to lots of data. The more quantity of data, even if this data is noisy, the more your very expressive models are going to stop overfitting and actually predict real features. So see what happens when we take exactly the same situation as before, and instead of having 100 data points, we keep everything the same, so the same kind of error bars and so on, but we go up to a large number, 10,000 data points. You can see now there is a scatter plot and it's completely messy. I cannot see anything over there. I see absolutely nothing. But if you give all these numbers to different models, linear, polynomial, third order, and 10th order, and then you ask to minimize the error, let's say that you make in your prediction, in your training, so you fit the best you can this very, very messy data, there is a qualitative change in your ability to generalize the model. With 10,000 events, although it's now completely messy and everything, but it's still so many events, all these features that the 10th order polynomial is trying to explain start being real. Some of them start being like true features of a 10th order polynomial. So when you try to see what's going on now with the fit you've done here and extend it to a larger range, now is the 10th order polynomial, the one that has a better fit in a larger range. The linear keeps as it is. It tries to just go straight ahead. Hence, when the data points start going up, because they do come from a 10th order polynomial, the linear does pretty badly. Then the cubic also does badly because it doesn't have the ability to actually express so much differences and changes. And it's the 10th order polynomial that we have fitted there that is able to predict to a larger extent what's going on later on. Look here, the 10th order polynomial is doing very well, and at some point, yes, it goes away and then runs down. But at least in that range, the 10th order polynomial is clearly the best. Where is the change? So we go from here, where it was doing a terrible job and not being able to generalize, to here, where it's able to go farther and do better than the others. The difference is the number of events. We have increased the data, and although it's noisy, this has led us to the ability to use more expressive models. So something to take into account is that when you start using machine learning techniques, let's say neural networks, they are extremely expressive. They have lots of parameters. And you have to make sure that your model is not overfitting. And sometimes for that, a simpler model, a simpler version of your, let's say, neural network with less layers and so on, might be a better way to go. Okay? With enough data, ideally, this problem improves. At some point, with enough data, although it is noisy, you are able to catch up with it. This is, again, very important for machine learning. Okay. So, summing up all this, I want you to remember that fitting data is not predicting. At some point, you will be able to use machine learning models that have a huge amount of possible parameters. And then your data set will be finite. And essentially, you will be able to fit any data set to a maximum perfection. I think here how this polynomial of 10th order can do lots of wiggles. Let me maybe show over here. Imagine now that instead of being a polynomial of 10th order, is a model that have hundreds of thousands of parameters. This is the typical situation you are going to find yourself when you use neural networks. So fitting is not predicting. You can fit anything with enough parameters, but you are not going to be able to predict what happens in new unseen situations. And this is what we care about. We care about predicting new situations. So what you care about is to produce robust models that generalize well. They go well from a decent description of the data you see to a decent description of data you have not seen. Using complex models, which will be the default in machine learning, will lead to overfitting, which is this #1 problem of rookies when they start with machine learning. Typical, like, I took a very complex thing, oh wow, whatever, medical diagnosis, and I get 97% accuracy first try. Yes, you get 97% accuracy, and then you are given new data images or whatever, and you do terrible because some little things here or there have changed, and that is enough as to confuse your neural network. And on many cases, simple models are better than large or complicated models, especially you are trying to describe small and complex data sets. So in data sets where you have many features, so many ways of thinking about this data set. If you use a complex model, this complex model is going to try to use all its expressivity to describe these very complex features. And again, fooling itself into thinking that is describing lots of interesting patterns that are not there, just because the data set is too small. So those features are fake. Okay, do you have any questions about this? If not, let me go ahead. Now let's write down the problem. We want to learn from data. We want to start with a data sample. This data sample is going to be called in-sample. That contains, for example, some inputs and some outputs. It's a collection of inputs and outputs. And by looking at it, examining it, modeling it, we try to understand, to learn relations between in and out, or given a need to predict an out in a new set of data that we call the out sample. To give you an example, imagine that you are trying to understand or to predict diseases based on, for example, medical images like these X-rays. To learn that, you need to first be exposed to lots of these examples where you are given an image and say, this image corresponds to this diagnosis, healthy, not healthy, or has a pneumonia, whatever. This other image corresponds to this diagnosis. This image, this is the way a doctor and radiologist will learn, is to actually sit down and look at lots of examples, and somebody tells him or her that there are these features over here that he should pay attention to, and so on. And the idea is, after all this learning from this in sample, the next time this person, this doctor, is produced or is shown a new image, is able to produce a diagnosis. And is able to realize that in this image, there are some features that are important that precisely led him or her to produce this diagnosis. That's what we would like to learn from data. Closer to home, let's say that you are a particle physicist, like we are, an experimental one, and you are trying to understand whether in the LHC collisions there are signatures of the Higgs, for example, of having been able to produce the Higgs. The way you will do that is to learn from lots and lots of real or simulated data that shows not only Higgs events, but also non-Higgs events, where you have an event with its characteristics and a label. For example, this could be event corresponds to digest production in the LHC, or dimuon production. Event corresponds to standard model production of Z. These events and so on and so forth. You will use all this data set and then try to fit it, so that produce a model and the best fit for that model, so that the next time you see an event, you are able to predict. So given the event, you will predict a label. So for example, you could say that this is a Higgs event where the Higgs decays into a ZZ, and it goes into 4 leptons. And the probability that this event is a Higgs event and not some other standard model background is, I don't know, 87% or something like this. So those are the kinds of learnings we would like to do. It starts with learning from labeled data sets and fitting to try to predict. And as you can imagine, it's extremely important that your fit, your model, is able to generalize to new situations. For example, that the way you are learning is not too influenced by, for example, the way you are doing your Monte Carlo simulation or things like this. So learning depends on the data, the amount of it, and the quality. And that in particle physics will be the amount of statistical and systematic errors that you have in your data. This, in the language of many machine learning reviews and so on, is called the variance of your data set. And the way you learn from this data depends on the model complexity that you have decided to put on it. So how do we interpret the data? In the example we've seen before of the different order polynomials, linear, third order, 10th order, is you, the person, the human, who decides to contrast data and models with a model of a given order. This is sometimes called a kind of bias that you introduce. You might want to interpret the data using very simple models, like a linear, or you might want to interpret the data with complex models that are able to capture many features. So as you can imagine, the results coming from these two choices, simple model, complex model, will be very different. And this is called a bias. And of course, there is always this underlying computational limitations when you are actually doing a machine learning analysis. You have limited resources, and also even at the level of what you are able to describe, how you are able to compute things depends on, for example, the architecture of your computer, or what kind of technology you are using, let's say GPUs versus CPUs, FPGAs, and so on. So there are lots of things to take into account. And by the way, lots of things where the human input is important and changes completely the results. Okay, so we have been talking about description of the data, what is a better description and so on. You already have a physical intuition of what that means. Typically, you think about how your description should minimize the error overall that you make on your predictions later on, right? So this is in this context is what is called a cost function. We are trying to decide whether we are learning from data, how well we are doing it. And typically that means trying to minimize the difference between what we observe and what we predict. The cost function is nothing but some functional dependence of this difference we are talking about. A typical cost function will be a square error. So over a data set that has inputs and outputs, you try to minimize this cost function that is given by the outputs, the observed outputs, minus the predicted outputs that are a function of the inputs. And you put this square, and that's the thing you're trying to minimize. Think, for example, on a chi-square fit. Many of you do this all the time, or some other more complicated form of a chi-square fit. What are those? There are differences between what we see versus what we expect in our model as a function of model parameters divided by some weight due to the errors, experimental errors of these measurements. And the idea is that we are going to minimize this cost function to obtain the specific values for these W's over here. So if, for example, if you say that your predicted outputs given inputs are going to be a function of your inputs with a weight and some bias, this function can be extremely complicated. Or it can be just linear. It could be that you want to describe the data that given some inputs, it's going to be a linear relation with the weights and the bias. But it could be extremely complicated and highly nonlinear, like we are going to see tomorrow. But in general, your predictions are going to be some function of the inputs and some weights and biases. So these parameters, weights and biases, are obtained, the best values for these parameters are obtained by minimizing the cost function. So the best model, the one that has the best description that minimizes the error or your prediction, is going to be given by looking at the cost function, which is this thing over here, and minimizing it. What parameters makes this error minimal? Now, this is simple enough to say. The best model then is the one that satisfies that the gradient of the cost function over all the parameter space of your weights is 0. In terms of this cost function as a square error, this is this expression. So you need to go over all the dimensionality of your data and try to find the 0 of this expression over here. The question is simple, it's nice, the interpretation is simple, but in practice, we need to devise a way to obtain these values of W, which minimize the cost function. And this is in general a very complex procedure because here we are in a course in machine learning. We need is advanced statistics in some way. And we are talking about a complex parameter of inputs and probably a difficult interpretation of outputs. This procedure also involves taking derivatives of a function that depends on parameters, and those, it better be that do not blow up. It better be that your procedure does not lead to getting stuck in a local minimum. You should not, when you are trying to find your minimum, hanging around and looking at this functional dependence, you should not hop too far and miss minima. primarily, you need to make sure that if you find the minimum, you find your best model, this will be the best model for the data you've seen only. So you need to make sure that when you run into that minimum and you give your predictions, don't generalize. Those are good when you go to other situations. And all this in a very high dimensional space. In general, this is extremely complicated, okay? This is what I guess the idea that I want to throw over here. But again, this is not the focus of this course. There are already lots of procedures that have been developed and studied and hard-coded so that you can just call them. You don't need to even code them yourself to try to precisely avoid all these pitfalls when it's trying to find minima. Because our situations are not going to be as simple as this plot over here, where you have a nice looking minima, and more or less wherever you start, you are going to little by little end up in it. And once you get there, you will get stuck in it, and then everything is groovy. No. Situation is going to be much more complicated. This is just in 2 dimensions. Imagine, or not imagine, because we cannot visualize it, but think about a higher dimensional space for X instead of being 2-dimensional, and a landscape of minima and maxima that is much more complicated. So that wherever you start, you might end up, depending on how much you hope, or, from one place to another, or what you take into account, not take into account, and so on, you might end up somewhere very far away, or actually bringing yourself into the minima. So there are lots of tricks that are used to make sure you hop into the right minima, as like stochastic jumps, which is the idea of adding some kind of thermal noise to your procedure so that you actually explore a larger parameter space, or doing an initial and very rough scouting of your parameter space, or when you are moving, trying to find your minima, use not only the difference between your initial step and the next step, but also the higher order derivatives or your cost function. The idea of batching, I mean, there are lots of techniques over there. You can go to, to go back. I have put a link to this review over here. This is extremely good, and I based the beginning of my lecture on it, where they explain in gory details all this stuff. But again, this is not the focus of this course. This is a practical course. It's based, case-based. We are going to learn how to do things, and that you need to be aware that those are problems and issues you need to handle. And often you also want to use regularization, which means as you are hopping around and you are trying to decide what is a better minimum or better situation, you might want to avoid the importance of some features. It could be, let's say, to put an example, that some features have large values, and those large values are then driving the whole fitting procedure to a particular point. So there is some features that artificially are bringing your minimum or your procedure to places that are not the true minimum. So the idea of using regularization is usually to avoid that some features dominate the fit. It prevents overfitting. It prevents the algorithm from focusing on features that are artificially large or artificially out there, and it tries to bring things to more standard and normal situation. So the 2 typical regularizations that we have, and then we're going to talk about, is this lasso and reach. Lasso, also called L1, and reach L2, is simply a thing that you add on top of your minimization procedure, which is trying to find the best model, means minimizing the cost function. Okay, so what you do is to prevent some of these features, some of these data values from dominating what's going on, you add an additional term regulated by this parameter called lambda that is either linear or quadratic with the weights. And what it makes is that it's trying to bring the minimum to values of omega, of w, sorry, equals 0. So it's preventing some features from getting coefficients, so from getting an importance that is too large. Okay, so this regularization is very typical. Any question here? If not, and again, you can interrupt me at any point, please do. Otherwise, I really feel like nobody is there and I'm just talking. So you survived up to now, so it's good. Let's move into more generic things that you need to learn, more language if you want. Then in machine learning, there is roughly two types of problems. One type of problem, and it's the typical that we encounter in physics, is a supervised problem where you are learning from data. You know that given some input, you get some output. Like in the example of the Higgs, you are learning from event and the label of the event. This is a standard model event, this is a Z event, this is a Higgs event, and so on and so forth, to later on understand relations between this in and out, and given an event, then being able to say, yes, that's Higgs, no, sorry, that's Z, or something like this. But in machine learning, because again, it's so powerful and it has this power of expression, you can go beyond the usual learning. You can do something that is called unsupervised learning, where what you give the algorithm to learn is simply a data sample. You don't give labels to this data sample. And then you ask the algorithm to find relations in data so that when more data is given to the algorithm, it finds similar relations. Let me explain this a bit, because this is maybe confusing. I think you understand the concept of supervised learning. Label data, you learn how to identify features, and then the next time they give you a data point, you'll be able to identify or give a probability for those features. But in unsupervised, we are given data like this with no specific instruction. There is no label on the data. So what the unsupervised algorithms do is to try to find patterns without instructions. So there are many, many unsupervised algorithms, but typically what they all do is to try to find a criteria for distance among the data points based on the features. And based on this distance, and this is quite broad as a definition, they try to find clusters of behavior. And having found a cluster of behavior, then also is able to detect things that are outside this cluster. In other words, is able to detect outliers or anomalies. So sometimes the distance to an unsupervised algorithm tells it that all these events are normal and this one is abnormal. But sometimes the distance tells the unsupervised algorithms that is able to cluster all these events of a type. This one is another type, very far from the other one. And then there is this cluster of behavior, this cluster of behavior, this cluster of behavior. Here, I think what we are seeing, I took it from the internet, but it's typical, right? This clustering. For example, you could think on Facebook users and think on the way they share things, they like or not like, what kind of news they click on, what kind of relations they have, or how many friends they have, and how many family members, the times they get in and out of a relationship, all this information which is multidimensional. And you just give a list of all these user and then characteristics of their behavior. And you can ask an algorithm, a supervised algorithm, to try to find people that are similar. Where similar could be anything. You don't give a criteria the similarities. You just say, try to find clusters of users. Try to find people that in some way that I'm not defining, but you will find these users are similar. And then you can start finding indeed users that because they share similarities one with another, then this kind of clustering can be exploited in a nasty way for marketing and so on. But you see, the power of these machine learning unsupervised algorithms is that sometimes you don't even need to give any kind of instruction. We will also talk at some point about genetic algorithms, algorithms where the criteria, for example, is survival. And you don't give any kind of instructions of how to achieve survival. Or reinforcement learning is another way of giving very, very vague instructions. You don't give an instruction, you give a goal. The goal is to survive, and the goal is to improve on that, and so on. And how you achieve it is up to the algorithm to explore possibilities. Another typical use of this supervision in terms of finding clustering is, for example, in computer vision. You can, for example, examine images, and the algorithm very quickly is able to identify that this is a cluster of behavior. It's called a person. This is a cluster, this is a cluster, this is a cluster, and so on and so forth. Why? Because of the color, the characteristics, the fact that it moves or it doesn't move, the edges or no edges, and so on. But you don't give these instructions. You just say, find me clusters of behavior. Segmentation in this case is what we are seeing, this image. And the segmentation is based on, you want this pixel, this pixel, this pixel, this pixel, they are all together because they are part of this person, which for you as a human is obvious, but for a machine it had to find a way of, in an unsupervised way, find this clustering. We are almost there for the, question?
Yeah, one question. Can you hear me?
Yes, I hear you very well. Tell me.
So what is the output of these unsupervised models or type of machine learning? Because if it only gives you the distance criteria, maybe you cannot treat this output as, for example, you are interested on sub-features of, I don't know.
You mean about how you interpret the clustering once the algorithm gives you a clustering?
Yeah, for example, if it creates different clusters automatically, but you were interested in features that are present in all of the clusters, but since it just does what it does,
Yeah.
you cannot extract these features, and it looks like the only output is this distance criteria, this distance among data points.
I think what you're pointing out is that you might want, and you are going to want to, as a physicist, you might want to actually not leave the algorithm just telling you, look, these guys are similar, these guys are similar, these guys are similar. You actually want to understand to some level why are they similar. When I say that machine learning algorithms are supervised or unsupervised, most of the time they end up being a mixture of both. So once the clustering is done, you go and try to understand what's going on. And when I say these evil applications, this is indeed the case. For example, Facebook will do this clustering, and companies will use this as a tool for marketing. And for that, they need to understand a little bit whether this is indeed what they are searching for. So when they, for example, advertise to a person over here, is it an efficient way of advertising to do it to people in this area, or this is not the real characteristic that we are looking for? And this I think brings us into this mixture between you do an unsupervised machine learning and then you do some supervision to actually understand what's going on. Same here, right? this in general computer vision is so easy to get because we are used to do this task all the time. For us, it's clear that if you see this image, the original image, you will know that this is a person, this is a post, this is a plant, and so on. You don't even try to then understand why the computer vision segmentation algorithm is doing this, because it's clear that it's doing what it should be doing. So it's clustering in terms of behavior. But yeah, there's like everything in machine learning, it's important that it does not become a kind of black box. And unsupervised is very powerful, but it's even more black box than supervision. So it needs to be taken with care. Any more questions?
But for example, when we were talking about Facebook and data processing of users,
Yeah.
it gives you different clusters of people, but you know that you have a goal to put this advertisement to a specific group of people. But
Yeah.
how? So you need to still have a treatment of the output to be sure what is the cluster you are interested in. And
Like, for example, when I say the Facebook and the customer optimization, it's because I know of Expedia, for example, use Facebook data to do clustering. And this then clustering was used to given, let's say, if I take all these clusters that Facebook is doing, and then I realized that many of my customers, the ones that actually clicked and went on, are, I'm saying this one, for example, they are most of them are here, or the majority of them are here. Then I have a bigger pool of possible customers I should be advertising to.
okay.
This, by the way, I know it happens because it's an experimental particle physicist who was working in Expedia and now is doing SpaceX. I think he's much happier now, but essentially he was doing these kind of things. I personally hate these things, but you know, this is what was happening. More questions? Okay, so supervision and supervised problems will be the most typical for you as particle physicist. And probably the first thing you want to do anyway is to use some of your physical intuition and label data sets to actually understand what's going on. And then maybe you want to jump into the sea and try to do something unsupervised. But typically you want to start with supervision. And then in supervision, you will have the data and the labels, the outputs, if you want, this that I always denote as Y. And the outputs can be of different types. It could be a continuous variable, or it could be a discrete variable. If it's continuous, you call this a regression problem. For example, X could be the inputs, could be the characteristics of PP collisions. How, for example, the protons are approaching to each other, and at the moment of collision, what kind of characteristics they have, and Y could be an output from this input, which will be the total number of events, the kinematic distributions that they lead to, and so on. So those are obviously continuous. Now, sometimes, quite often, in fact, the outputs are not continuous. What you want to do is to label, to say whether you're given a set of inputs, what kind of classification you can make. In this case, this is called logistic regression. It's a problem of classification. So it could be that given the characteristics of an event, just to go back to particle physics, you want to then decide whether this could lead to a B tag or no B tag, or a quark or gluon jet, or whether this will lead to a mostly electromagnetic or mostly hadronic. These are labels that that are discrete. B tag, let's say, is 1, no B tag 0. Quark or gluon is binary, is either quark or gluon. Electromagnetic or hadronic, and so on. Those kind of discrete outputs leads to this problem of classification, which is very, very common, especially in machine learning. But coming back to this medical application, there we were also talking about a discrete problem. Given an input, which is these images of X-rays, the outputs will be the diagnosis, which is a discrete label. Discrete, although it could be complex. It could be that somebody healthy or ill. It could be that ill means that it has such and such and such disease at the same time, and so on. But it's discrete. That's what I mean. It's just something that doesn't take continuous values. The simplest classification problem, and here I'm just going to say it very quickly because that's what we are going to discuss tomorrow, is a binary problem in which, given a data set, we have the inputs being whatever, PP collisions, X-ray images, and the outputs is the classification, is yes or no, like is big tag or not big tag, or the event you show me is new physics or a standard model. In that case, this logistic regression, what it will give you, or what you want to obtain as a cost function, is the probability that a data point is true or false. And this probability is either is true or either is false. The function that leads to this kind of probability is a function that needs to go from 0 to 1 because it's a probability. And for example, you could imagine functions that go from 0 to 1 as many types. For example, this is called the perceptron, which is given the inputs and their weights. And depending on that value, I can get 0 or 1. You can have a sigmoid, which is something a bit more softer if you want, that across the boundaries and so on. I'm not going to spend time here because tomorrow we are going to study neural networks. The building blocks of neural networks I told you on Friday were neurons, and the neurons are based precisely on this binary classification problem. So we are going to go through this in detail. So just a heads up that we are going to talk about this tomorrow. So tomorrow we'll talk about the binary problem as a basis to understand neural networks. And what we are going to do today, so for the rest of the class, is the following. So we will work an example of a multivariate linear regression. So the idea that our description of the data will be some linear relation with the inputs, and the amount of inputs, the dimensionality of the inputs, is bigger than 1. So it has more than one variable. The way to do this will be with a tool called scikit-scikit-learn, and just writing it there because you are going to look at this and learn a tiny bit what it's about. And I'm giving you a notebook to start playing. This notebook takes a data set. This data set is of the amount of bikes that have been rented in Washington, D.C., with the data given by the seasonality, the temperature, the humidity of the day, the wind speed, the hour, the day, lots of different variables. The idea is that with this data set, one should be able to predict to some extent, given some day of the year, time of the day, temperature, humidity, wind speed, and so on, how many rides you should expect that day. And that will allow, for example, the company doing the bike ride sharing scheme to predict and to also bring enough bikes to different positions, essentially. The way we are going to do this is using simple data manipulation in pandas, data visualization in matplotlib and Seaborn, and we will also learn about L1 and L2 regularization. How do you actually implement that in a very simple setup? Now, this day is going to be a bit hard if it's your first time with all this stuff, but I'm writing in capitals all these things, scikit-learn, pandas, Seaborn, and so on, because there are things that are going to appear over and over and over again as tools that we will use to manipulate data, to visualize data, to call for functions that do analysis and so on. So today I will say spend a lot of time looking at the notebook and trying to understand what is in it. Okay. So the idea is that you link on it, click on this. It will bring you to Google Colab with a notebook that you will see is mine. I'm sharing with you, and what you need to do is in File, save a copy and play with it. When you start running into trouble, if you do, send questions in Slack to everyone, okay, in the section of notebooks. And probably it will be more likely that somebody else answers this question than me, okay? There's so many people in this course, and I'm sure many of those will know a lot about machine learning already. So please, guys, if you see a question and you know the answer, participate on that. And we will reconvene at 12:30. Now, to me, it's very important that you, to some level, engage with the course. So if at 12:30 I don't see enough people and nobody is speaking, tomorrow I'll give you the lesson and I will not give you an example notebook. So you will be on your own, okay? I really think it's important that you make the effort during this time to actually look at the notebook and try to extract something from it, and that one of you at least talks every time that we reconvene and explains what they've done, what they understood, the problems they had, and so on. Otherwise, I could just record the lectures and then you can look at them whenever you want. This is an intense course and you're going to end up this week learning, okay? Sorry, I sound a bit aggressive, but it's just, please, if at 12:30 I don't see enough people and nobody speaks, really, that will be the next step I will take, okay? Just one last thing. When you click on this, it brings you here. It takes time, apparently. One thing is that there's this over here. You see, I'm calling from Google Colab, import my drive. It means that you have a drive in Google. And this is mounting this drive. And it took me like years to realize this. Not years, but it took me some time. When you click on it, the first time, it's taking time, but by the way, can you see what I'm doing right now?
Yes.
Perfect. So for some reason, because I'm really not good at computers, so I spend a lot of time looking at this and thinking, because I don't read things. But essentially what it says is, click on this. It clicks. You need to enter into your Google Drive thing. Then you copy this. Let's go back. You paste it here, and then you click again. And then mounts your Google Drive. Okay, it's just that since it took me so much time to realize this, I want to make sure you don't have the same problem. So remember, you open this, go to File, save a copy in Drive, and you start playing with on your own, or you can download it locally and then use it locally as well. The data set is from Kaggle. You could sign up for Kaggle. Kaggle is essentially a kind of data set repository and a place for competitions where people in data science are given from time to time let's say a challenge, and sometimes these challenges are for money, essentially, like here. I don't know if you can see this. Here, the open competitions, the first one that we see is trying to find a classificator or something that classifies comments as toxic, and whoever is the winner will get $50,000, or some company is offering $50,000 to whoever is able to predict with more accuracy Walmart unit sales or stuff like this. Or there are things that are a bit more interesting, for example, like in neuroimaging and so on. So anybody can sign up for Kaggle for any of these competitions, work in groups, and then compete. And if they win, they get this money, I guess. I've never done it, so I don't know. But that's Kaggle. So you can, or Kaggle, sorry. And you can sign up for it. And for me, the interesting thing is that it has lots of data. And for each data set, there's typically lots of, let me say, open one fake and real news data set. When you go to any data set, there will be the data you can download. There is also what is called the kernels. And the kernels is people who have been trying to solve these problems, share their solutions, and then they are upvoted. So if the solution is really good, they get upvoted, and then the higher the votes, the more useful this solution is. So it's a very, I don't know, it's an interesting idea. In case you don't want to sign for Kaggle in order to get the data, no problem. I just put this data in my Dropbox, so you can click on this link, you get the data. It's simply a CSV, so it's a spreadsheet of things that is the daytime, the season, type of holiday or working day, the weather, temperature, and so on. And I have put here what the meaning of each of these variables is. And then you will see there are lots of examples of what you could do and a bit of discussion and so on. So for me, if I were you and it's the first time you see all this, just make sure you can run the notebook so that you have everything that you need, and then you start and try to understand some of the things that are done over here. And again, it's the use of pandas to deal with data, the use of matplotlib and Seaborn to visualize data, like we are doing over here, and the use of sklearn in order to do linear regression, correlation matrices, and so on. Okay, so it's three components there: data handling, data visualization, and analysis, that it will be good that you see a bit. Okay.
Veronica,
yes.
So if we want to run this on, with Conda or whatever locally, so what happens with the first? Well, I tried and then it gives me an error. So I guess this Google Colab, it doesn't ask me, it doesn't give me the opportunity to go to this Google account and get this password.
Yeah, so, you go to your root locally is easier. Remove this, don't do this. Okay. But make sure that in the same directory you are in this data set, you have downloaded it. It's just a simple file.csv. It's a spreadsheet with numbers. Okay. And then the rest, for example, the first time you run this with this import pandas, import numpy, imagine that you get an error. It says, we don't know what Seaborn is. So you just go and say conda install Seaborn. Okay. We don't know what numpy is. Conda install numpy. And that's why having Anaconda is useful, because you can install locally anything you want quite fast.
Okay. I try. Thanks.
And any questions, please, place them in Slack. If this is your first time, you are going to run into trouble. That's normal. But tomorrow will be easier. The next day will be easier, and at the end of the week, you'll be an expert on doing all this. Okay? But ask the questions and don't get stuck without asking. Okay?
Can I say something, Veronica?
Yeah.
Just for people using the Colab, just downloading the CSV is not enough. You have to upload the CSV in your Google Drive for it to work. Okay. So you create a folder. You see the name in the third cell. You create a folder called bike sharing dataset, and you upload the data, the CSV file you download inside that folder in your Google Drive. Otherwise, it doesn't work.
Exactly. So this is working inside Google Colab, and it links to your Google Drive. So if the file is not there, it's not going to see it. Thank you, Roberto. That's a good point. But again, any questions through Slack? Okay, so we'll reconvene in a bit more than an hour. Don't stress. Again, it's just I want to make sure that we all reconvene, that somebody speaks a bit, and I make sure you are actually engaging with at least looking over these simple notebooks. Okay. Any more questions? If not, I'm going to stop.